Okay, so let me introduce the next speaker, who is Hanzhang Wang. He is going to talk about JavART or something else, a lightweight rule-based JIT compiler using translation rules extracted from a learning approach. So let's start.
Okay, thanks for introducing. Hi, my name is Wang Hanzhang, and I'm glad to present my talk here. And the title is JavART, a lightweight rule-based JIT compiler using translation rules extracted from a learning approach. Well, applications and the applications framework layer of the Android system written by languages such as Java and Kotlin. So they need an Android runtime system to execute this code on various hardware devices, ranging from TV sets, watches, tablets, and even automotive systems. So just like Java virtual machine, the execution engine of the Android system uses a multi-tier execution consisting of an interpreter and 2 tiers of compilers. Now we've done some small measurements about this. So suppose it takes 1 microseconds to execute a method by the interpreter. Then it will take around maybe 341 microseconds by the baseline compiler to achieve 6 times speed up. And if we finally compile it by the optimized compiler spending around 800 microseconds, it is further speed up to 40 times. And now the execution time is cut down to 0.07 microseconds. Now, if we drop this time cost into a curve, it will look like this. The x represent the compilation cost, and the y represent the execution cost. And this curve is somehow called the Pareto from tiers in the language virtual machine research area. So we've run 9 apps on Android and the phone, and we run them for 2 to 3 minutes. And after each run, we measure the CPU cycles to evaluate this. And we found that around 1/3 of the CPU cycles is taken up by the interpreter in this short running scenario. So we want to point out that in this short running scenario, the warm-up issue is quite considerable. So our goal is here to try to cut down the compilation overhead and bring the optimization earlier. Speaking of fast compilation, there's some existing solution named the template JIT, where typically it translates 1 bytecode at a time into a native code template. It is fast, but it performs no optimizations. It only eliminates the dispatch overhead in the interpreter, so the code quality is not so satisfying. Our observation is that if we put the bytecode and the compiled native code together, we can find there's some mappings between them. And if we can learn these mappings into a form, we call it a translation rule, we can use it to establish a rule-based compiler. Well, this rule-based compiler works more or less like the template JIT. You can see it performs a rule matching process, which can be fast, but at the same time, it translates a bytecode sequence at a time, so it can apply the learned optimizations from the existing compiler. So we can get good code quality at the same time. Now, here's our workflow. It is subdivided into an offline learning process and an online applying process. The learning process, we first do code extraction to produce some rule candidates. Then we do a technique called parameterization, we will introduce later, to produce more rule candidates. Then we verify the translation rules to guarantee the correctness. In the applying process, we first match the incoming bytecodes with the translation rules. Then we perform a lightweight register allocation to map the virtual register to the physical register. And finally, we do the code generation to handle some native code level details. So here's how we produce some rule candidates. At first, we compile the bytecode methods either by the baseline compiler or the optimized compilers. Then we slice the code blocks according to the metadata left by the compilers. These metadata left by compilers are used to tell the locations of the bytecodes in the native codes. For example, here, the second bytecode, the if GE, the compilers will tell us it is mapped to the b.ge, the fourth instruction in the native code. The next step is the parameterization, is that we have some rule candidates already, and we want to produce more rule candidates to have high code coverage. And for example, the AND, OR, and XOR operations, they all perform on 2 source operands and store 1 result to a target operand. So suppose when we already have a rule for AND, such rule also holds for the OR. And also the integer constant doesn't need to be fixed. It can be any immediate numbers. Next, we want to verify the translation rules. If we look at the raw rule here, the very first things, we have no idea how to use these rules. So let's first define what is correctness. Well, we first want to have the appropriate operand mappings. This means we want to answer the question that what operand does V0 here represent? Does it represent R0 or does it represent R1? This is the first question. And the second, once we have the operand mappings, we want to know that whether they are operated in an equivalent way. So here's an example showing how this works. First of all, we enumerate all of the possible mappings. Here we mapped V0, V1 to R0, R1, or in the reverse way. And next we perform a symbolic execution to execute this code. And since we already initiate the input values, we will compute the output values. And next, we feed the results to an SMT solver to check the correctness of these equations, and how these equations are written are according to the mapping schemes as before. So here we have to have the first operands mapping schemes to be correct, and this rule is usable. And in other situations, if we enumerate all of the possible mappings but still cannot find a possible one, such rule is discarded. And after we establish usable translation rules, we match the rules to establish a JIT compiler. We map the codes in a sliding window. It looks like this. Suppose we have a for code block here, and first of all, we use all of the code to hash search to find the appropriate rules. And once we fail a search, for example, we will decrease the window size by 1 instruction until we find one. And after we matched a rule, we proceed this process to the next instruction until all of the code has been matched. Next, we perform a register allocation. This is like a block scope linear scan allocation. And however, we only need to scan through the instruction in one pass. So our paper has more details about this algorithm. If you have interested in it, please have a look. The next step is the code generation. We handle some native code level details. And also, we have to handle some stacks, for example, the stack maps, which is for garbage collection, and inline caching, which is for virtual call, and we handle some ISA constraints. For example, the ARM64 will have constraints on addressing mode, memory addressing. We evaluate our system on Google Pixel 7, equipped with Android 14. Both of them are released in 3 years. And we include 9 real interactive applications. They are script-driven workload in 2 to 3 minutes. And we measure metrics like CPU cycles and frame drop rate. Frame drop rate here refers to the slow UI rendering the user might suffer from, since the performance is not good. And we also include benchmark weights. They are highly repeatable and deterministic. Well, this is very crucial to measure the peak performance of the virtual machines, since we have to iterate the benchmarks hundreds times again to reach a steady state, which can be finished in a command line. Well, first we present the data of the execution speed. Well, if we look at the bar here, it is relative to the interpreter, which is the black bar here, and our work is the blue bar. We can see that our code quality is on par with the baseline JIT and slightly better, but it's not comparable to the optimized JIT, since it performs aggressive optimizations such as escape analysis, loop transformations, and many aggressive inline. These optimizations cannot be finished in just a room matching process. Next we present the compilation speed, which is relative to the optimized JIT, which is the slowest. And well, our code generator will translate quite faster than the baseline JIT and the optimized JIT. So compared to the baseline JIT, the execution speed is 6% better, and the compilation speed is quite faster. Next, we show the overall performance, which is the multi-tier performance. And we measure this by the CPU cycles on the real applications. And the default mode in the Android system is the interpreter with the 2 tiers of compilers. And the first 4 bar here, we want to show that either we turn off the baseline JIT or turn off the optimized JIT, or we just use the optimized JIT to replace the baseline JIT. They all turn out to have regressions. So it is reasonable to compare to the default mode. The default mode is well-tuned. And the improvement of our work is 20% reduction on the CPU cycles. And the main benefits come from our work is originally the CPU cycles taken up by the interpreter. We have shown before it is 1/3 of the total execution CPU cycles. And how do our work improve the user experience? Well, this is measured by the Janky frame rate, also known as the frame drop rate, where we report a 50% reduction on the frame drop rate. And this metric is more or less related to the CPU cycles. So in summary, our work presents a framework of the lightweight rule-based compilation and an automatic learning approach to generate translation rules. We evaluate our system implemented on Android 14, and compared to the baseline JIT, our compiler can generate code 5.5 times faster, with the running code 6% faster. And integrate our compiler in the total system, the multi-tier execution will achieve a 23% improvement on the program performance. And that's all for my work. Thanks for listening.
If you have questions, please come up to the microphone.
Thanks for the talk. I have a few questions. The first question is that I wonder how you handling the conditional flags, because in x86 some operation may implicitly set the conditional flags.
Conditional flags.
For example, when you sub to, for example, A sub B, and for example, sometimes if the result is negative, then the conditional flag will be implicitly set.
Okay, that's an interesting question. Those code in ARM64, they are, in practice, they are placed at the block boundaries to link the basic blocks. So we need to handle them when translating the branch instructions. So,
no, I mean during the learning phase. And this will influence the semantic of your translation rules.
Translation rules. You mean the,
yes.
For example, the compare v0, v1, and compare.
Yes.
They can be, we implement how to verify them in our verification. So the conditional flags set by compare. These code are verified together with the b.ge, together with the if GE. So the when compare happens, it will set up the conditional flags, and we can finish it by the execution engine.
Yes, then the second question is that how you align the operands when you learn the rules?
Align the operands?
Yes, you mentioned that you will slice them, and
we just enumerate all of the possible operand mappings, and until a correct operand mappings will trigger a correct equations results, and we will know how the operands are mapped.
So do you have the evaluation of your time performance?
There are some data in our paper.
Okay.
I can tell it's around 5K rules in 10 minutes.
Okay. Final, a small question. Do you have the coverage analysis of your algorithm? I mean, the coverage of the instruction set.
Most of the code, all of the code will be covered, since we have prepared some rule for some complex bytecode. For example, the invoke instruction, we have to manually prepare some rule template to achieve 100% coverage. So all of the code can be translated.
I see. Oh, thanks.
Hi. Did you discover any limitation where you couldn't implement the optimization you wanted to achieve? Or do you think it's possible to achieve any optimization by parameterizing as you need, I guess?
Yeah, since the learning scope is quite limited, so many optimization cannot be achieved by this algorithm. For example, the loop transformation and some code scheduling, they will be hard to be achieved by this approach. So it can generate a code at a quality, for example, maybe slightly faster than the baseline JIT.
Okay, thank you.
Thank you.
Short question, please.
Okay, quick question. So why your TLJIT is effective in Android?
Sorry, can you repeat?
TLJIT.
TLJIT, what?
It's effective. Why? Why?
Why is TLJIT effective?
Yeah.
So you mean why we used the optimized JIT as the second tier? Or?
Okay, yeah. So what?
since we have to add the optimized JIT to do further optimizations.
Oh, I see.
Yeah, since many optimization cannot be achieved by our tier.
Okay, so let's talk later.
Thank you very much.